recording starts. So thanks for coming back, everybody. I sent out an email this morning just saying that I will not be available for office hours tomorrow. I have a family commitment, but instead what we'll do is I'll move that office hour to Monday at 2:30. And then what will happen is that the homework, which is usually due on Monday, I'll delay that to Tuesday so that you have an extra day after the office hours if you're still working on problems. So I apologize for the inconvenience. Like I said, there's kind of a family thing. My wife and kids were going to Seabreeze, which I suppose is a water park here in Rochester. So we're going to check it out. I'll report back, I guess, on Monday, let you know how it goes. Any questions or concerns about moving that office hour time? Okay, thanks. So today we're going to move away from internal combustion engines. So like I said, we're moving quickly through this back third of the class. So again, I think it's really important to sort of focus on what's the process for doing all these cycle analysis problems so we can think about them all as being the same problem as opposed to trying to memorize, however many it is, 6 or 8 different cycles. Right? So today we're going to talk about Brayton cycles. Here's a picture of a Brayton cycle power plant. So Brayton cycles, as I'm sure we'll talk about as we move through the class, so they're sort of like the up and coming energy source here in the US. Maybe you've heard lots of debate or discussion about coal power plants and gas power plants. So Brayton cycles are how we use a fuel like natural gas to generate power. So the nice thing about this is driving the reduction in emissions that we see here in the US. Most of the gains the gains in emission reduction, maybe there's a better way to say that, but is driven by a move from coal to natural gas. Now, as with any method that we use to generate energy, there are downsides. You potentially also heard about the discussion of fracking, which is generally how we get the natural gas out of the ground. So there are difficulties doing that as well, or challenges anyway. And so, we need engineers on all sides of these kind of issues trying to, come up with new solutions to do things like reduce emissions. But then also you need engineers on the other side saying, well, how can we do things like get natural gas out of the ground more efficiently, right? So there's lots of problems for us engineers to be solving, right? So this is from 2019. So Brayton cycles in 2019 make up almost 40% of the power generation that we have here in the United States. So, and this number is rising. So unlike when we talked about the Rankine cycles where that number is decreasing because we're trying to decrease our reliance on coal, we're trying to, supplant that coal power generation with natural gas power generation. And doing that involves using Brayton cycles. And as we'll see, the Brayton cycle also ends up being the core of a jet engine as well. So why do we care about Brayton cycles? So they're sort of the workhorse for these natural gas fueled power plants, right? So like I said, about 40% of the energy in 2019 anyway was produced using these Brayton cycles. And then as we move on from Brayton, the next thing we'll do is turbojet engines. And we'll see that the turbojet engine is mostly a Brayton cycle. Just with a little bit of dressing up on the inlet and the outlet. So gas turbines are good because they're faster and cheaper to construct, particularly if you're comparing them with something like a nuclear power plant, which involves significant amounts of construction that takes a long time and is extremely expensive. The United States has large shale deposits, so basically there is a lot of natural gas available to us here in the U.S. So sometimes you'll hear politicians talk about things like energy independence, meaning that we could produce all the energy that we need with resources that are here in the United States. So this is at least one argument for moving more to gas power plants. Now it's up to you, like all arguments, how much you buy into whether or not you like that argument, right? So natural gas power plants or Brayton cycles are used in power plants, like we've talked about, but also in vehicle propulsion, right? So if you're thinking about joining our aero stream of mechanical engineering, then you might be interested in how we'll end up using Brayton cycles to power jet planes. There are definitely cons to using Brayton cycles. So even though moving from coal to natural gas reduces emissions, it doesn't bring us to zero emissions, right? So there still are CO2 emissions when we're burning natural gas, although they are reduced from coal. And then we also have challenges potentially with extracting natural gas from the earth. We typically use a process called fracking. And, particularly around here and in Pennsylvania, I think so there's always political discussions about sort of the safety and the effectiveness of fracking. So it's beyond the scope of this class, but like I said, engineers are needed to solve all kinds of problems across all kinds of different application spaces. And certainly if you're interested in something like that, that's a problem that mechanical engineers can certainly contribute to. So this is what a Brayton cycle looks like, right? So it's a little bit, it's kind of like got 1 foot in the same space as Rankine cycles and 1 foot in the same space as internal combustion engines, right? So it's like a Rankine cycle because it's a series of open systems, right? So we're bringing air in just from the environment. We compress that air. And then when it's at a high pressure, we add fuel and combust the fuel, right? So we're adding heat here. And then we have high pressure, high temperature gas, which we run through a turbine. It wants to expand over those fan blades, and that makes that fan spin. And because it's connected to a shaft, that gives us mechanical work. The cool thing, or one cool thing about these Brayton cycles, is that the same shaft that spins in the turbine is also spinning in the compressor. So you sort of have direct drive of the compressor from the turbine. So you can have these things put together on the same shaft so that, again, once you've started it, starting is always sort of an issue, just like you need a starter motor in your automobile, right? You need some way to get the thing going. But once it's going, then the power from the turbine is sort of directly linked to the power consumed by the compressor by that mechanical shaft. So like Rankine cycles, there are open systems, right? And but sort of like internal combustion engines, we'll assume that the working fluid is an ideal gas, typically air, right? So even though, again, that's not true, just like it wasn't true with internal combustion engines, we have some working fluid that's in reality changing because we have air coming in, then we put fuel in it, then we combust the fuel, and then we have this spent air fuel mixture that we exhaust out. Typically, these systems are open to the atmosphere because we're bringing in new air all the time because we need the oxygen. Because without oxygen, we can't combust the fuel, right? So that then, the sort of exhaust products are expelled out into the environment, right? So this is when we talked about how a power plant like this actually does have emissions, even though the emissions are lower than they are with coal. Right? Now, sometimes we'll model it as a closed system, and I suppose in reality there may be actual systems that run like this. But here, this is assuming that we just have air and we're not doing any combustion. So instead of having combustion and then exhaust to the atmosphere, we have air that's running around in this cycle, and we're adding heat up here instead of burning something, right? And then we go through the turbine. And then we cool it off, right? Because Kelvin and Planck told us for every heat engine, we need a heat sink. So we cool it off here, then we compress it, then we add some more heat, and we just keep going around and around and around, right? So it's like a Rankine cycle because we'll use the open versions of the first law and the second law, but it's like an internal combustion engine because when we ask ourselves, what's the fluid? Well, the fluid is air, right? So the air is an ideal gas, so we'll use the same strategies as we did in the internal combustion engine, which means that we have to look for those isentropic processes. So, keep in the back of your head, we're going to be looking for ideal compressors and turbines to use either an expression that's got a VR or a PR in it or a K in the exponent. So this is what happens, right? So we have air and we pull it in. It goes into our compressor. The compressor is like a pump. It's just we're using it for gases instead of liquids. Its job is to increase the pressure of the fluid. So it raises the enthalpy of the fluid by increasing the pressure. Here we're putting work in. Right? Now, the air mixes with the fuel in the combustion chamber. I like that one, right? With the dots. I took this one from the textbook. I can't take credit, but I think it looks nice, right? So now we're mixing with the fuel and we're burning it, right? So this is the combustion chamber. So this is like adding heat, right? It's like the boiler in the Rankine cycle, right? But here it's actually happening in the fluid, right? But we're going to assume that there's no change in the chemical composition, that something like the specific gas constant doesn't change. Then we have this high temperature, high pressure gas, right? So this is air now at high temperature and pressure and not steam. And it's going to want to expand. I mean, not that it has a brain, but it wants to expand, right? And then it expands over these turbine blades, and that makes that puts some torque on this shaft, which makes the shaft spin. So we get power, right? And again, we make friends with an electrical. This power, some of it goes to the compressor mechanically. We don't need an electrical engineer for that. But we're also going to have this shaft spinning, so we got to be friends with an electrical engineer who's going to say, oh, I can put a generator on that spinning shaft, and that'll give us electrical power, which we can put out onto the grid. Right? So that's kind of, in a nutshell, how these Brayton-type cycles operate. So there's always more air coming in, and there's always air going out. Right? So this is just what I talked to, that the turbine and the compressor can be mechanically coupled on the same shaft, so that, when we talked about the Rankine cycle, it was the plug for the pump was plugged into the into the grid, and the turbine was putting power out onto the grid. So, that power got to the pump, through electrical wires. Whereas here, the mechanical power generated by the turbine is directly transmitted to the compressor because of this solid shaft that can connect both pieces. Right? But that doesn't use all, if that consumed all the power that we generated in the turbine, it would be better not to run the system, right? So we have to have some surplus power, and that's going to be our network, which goes out onto, connects maybe to an electrical generator and goes out onto the grid. So where do we get our heat from, right? So typically, this is, the big use for these Brayton cycles is natural gas power plants. So typically we're burning natural gas, right? But you could also be burning other types of fuel to use these Brayton cycles, things like biomass or municipal solid waste, which apparently is hard for me to say. You can get a waste heat from an industrial process. So maybe you have a Rankine cycle, right? And remember, we talked about one of the downsides to the efficiency of a Rankine cycle is that cooling that steam down to a liquid means that you're removing a lot of heat. But we could, just like when we talked about in the textbook, when we were talking about ideal cycles and stacking them on top of each other, if we use the waste heat from something like a Rankine cycle and put that into a Brayton cycle, then we're wasting less of the heat, because then some of that heat will run through this Brayton cycle, while all of that heat will run into the Brayton cycle, and some of it will be turned into work, right? So we can change, we call that cogeneration. That's beyond the scope of the class, but you can read about it in the textbook. And maybe if you take Thermo 2, which I believe is an option downstream, I think they talk about cogeneration in Thermo 2. You could get heat just from solar power, right? A gas-cooled nuclear reactor. So again, with a nuclear reactor, you got to cool the thing off somehow. So, like any waste product, right? If you want to be better environmentally, typically what you try to do is you try to look at the waste product of whatever process you're running and say, like, can I use that waste product for something else, right? So if you're cooling a nuclear reactor, then, with gas in this case, then maybe that's how you add heat into your Brayton cycle. Right? So if we think about this as a closed system instead of an open system, right? As a series of closed systems, right? Because here, when we say closed, we don't mean that closed in terms of the internal combustion engine. We mean that the whole system is a closed loop, right? So if you hear someone talking about an open Brayton cycle, what they mean is that this heat exchanger doesn't really exist, that you're pulling air in from the atmosphere and you're exhausting air out to the atmosphere, right? So here, when the textbook talks about closed turbine power plants, right? So closed Brayton cycles, they just mean that there's an actual heat exchanger in here instead of in the other way where we're just sort of using the environment as that other heat exchanger, where we're putting hot air out into the environment and taking cool air in, right? So here there's actually 4 components, right? So this is kind of like the 4-component, the original Rankine cycle that we learned also had 4 components. The compressor, which is analogous to a pump, right? The heat exchanger, which is like the steam generator. The turbine, which is like the turbine, right? And this heat exchanger here that's rejecting heat, which is like the condenser that we had in the Rankine cycle. But we don't use words like condenser here because there's no liquid, right? It's not steam. We're not condensing anything because we're just using gas. So we're just making the gas cooler, right? So here, if it was a case like this, then we have our little air molecules and they just keep running around and around the circle. To do this, if you're doing this in reality, you need to be getting your heat from some external source. You can't be burning fuel inside your cycle if you have one of these closed versions of the Brayton cycle, because every time you burn something, you consume oxygen, right? You're turning oxygen into carbon dioxide, and then that means that there's less oxygen to burn the next thing in, right? So here you have some external heat source, and then you have a heat exchanger at the bottom where you're rejecting heat, right? So if we look at, remember I said that we can, if we think about solving all these problems in the same way, then we kind of got to ask ourselves 3 questions, right? The first question is, how do we characterize the cycle? So far, all the cycles we know are characterized in the same way because they're all heat engines, which means that the main characterization parameter we're looking at is thermal efficiency, right? We take the energy benefit, which in this case is net power, and we divide by the energy cost, which is heat going in. So this is the same as a Rankine cycle. Then we ask ourselves, when I go through this cycle, is it going to be a series of open system processes or a series of closed system processes? Basically, which versions of the first and second law do I need to use? And like the Rankine cycle, this is an open system process. So far, it's exactly the same as a Rankine cycle, right? But the difference comes on the third question, what's the fluid? Because the Rankine cycle, remember that the working fluid was water, right? So we were worried about liquid water, and then we're boiling it, and then we're condensing it back down, right? We don't do that in a Brayton cycle. In a Brayton cycle, it's always a gas, right? So it's not changing phase, right? It's some ideal gas. So here, we're going to do the analysis, right? The symbolic solutions will look very similar to what we did for the Rankine cycle. But when we go and ask ourselves, what's the fluid? Remember, that's the question we ask ourselves when we're trying to say, how do I fix the state, right? When we ask ourselves that, well, then it'll look more like an internal combustion engine, right? So we're going to use things like the ideal gas law. We're going to look for isentropic processes so we can use those special isentropic relationships. Maybe we'll have to use table 822 to find things like PRs and VRs and U's and H's, right? And S superscript zeros if we have to do some second law stuff, right? So this is the difference from the Rankine cycle, right? This is what makes it a little bit like an internal combustion engine, right? So 2 of our 3 questions are the same as the Rankine cycle, but one of them is different, right? So how we fix the states is going to be different. So because the working fluid is air, which is an ideal gas, we're going to make a lot of the same assumptions that we did when we talked about internal combustion engines. We're going to neglect combustion. We're going to talk about this always as if heat is coming into a heat exchanger, as opposed to us injecting fuel and then burning it and worrying about that sort of chemical reaction and the changing in the gas. Right? Unlike the internal combustion engine, we're not going to assume that it's a closed system. Right? So all of these systems will be open system processes, and we will use the open versions of the first and second law if we need them. We're not going to assume that all processes are reversible, but knowing where potential reversible processes are, right? So knowing what an ideal compressor and an ideal turbine might be is going to be important for us, right? But then we're going to add on the isentropic efficiencies we talked about when we were talking about Rankine cycles, right? So we're still going to know we're going to have to use the ideal compressor in the ideal turbine. The working fluid, we're going to say, is an ideal gas, that it's always air, right? So we're not going to deal with any kind of chemical changes to the working fluid. And sometimes, like I think in the example that I'm going to do today, we will also assume that it's constant specific heat. So anytime the fluid is an ideal gas, we have to ask ourselves, oh, is it constant specific heat or is it variable specific heat? Basically, if it's constant specific heat, I can use equations of Cp, Cv, and K in it. But if it's variable specific heat, then what I have to do is I got to use table A22, probably looking up things like PRs and VRs and Hs and Ss, as superscript zeros on that table. So here's our Brayton cycle, right? This is the open version of the Brayton cycle. Even though it's open, right, and there's no actual heat exchanger here, we're going to pretend like the rest of the environment acts like a heat exchanger. So we're going to model it as if there was this heat exchanger where we have this dotted line, right? So, there's always air coming in and there's always air going out. And then that air going out is just kind of, ultimately circulating in the environment, and we're going to pull some air back in, right? So if we want to know how much heat is being rejected in the system, then we would run a first law analysis on this, pretend heat exchanger that's really just the environment, right? So we'd have to make some assumptions, and we'd probably get something like Q dot out is equal to M dot times H out, which is H1, minus H in, which is H4. So how do we characterize the cycle? Typically, the most important characterization parameter for heat engines is thermal efficiency, where our desired energy effect is net power, and our energy cost is heat transfer into the system. How much natural gas that I have to burn, right? Because we're not splitting up the mass like we did in Rankine regeneration, the mass flow rates in all of these processes are going to be the same. We also talked about, when we talked about Rankine cycles, this thing called backwork ratios, right? So backwork ratios kind of recognizes that the power plant is the first consumer of the power plant, that not all that turbine power can go onto the grid, that we need to save some of it just to run our cycle, right? So backwork ratios for these Brayton cycles tend to be higher than they are in Rankine cycles, right? Maybe on the order of 20% instead of on the order of maybe 1 to 2%. But because we reject less heat, because we don't have to condense a fluid, then we typically can get higher thermal efficiencies with these Brayton cycles, right? So here our backwork ratios tend to be higher than they are in Rankine cycles. And that's because, remember that part of the benefit of running the Rankine cycle was that it's comparatively easy. It doesn't take much power to increase the pressure of a liquid, right? Because it's incompressible, right? But compressing a gas is hard because those gas molecules will kind of scrunch up, right? So it takes more power to increase the pressure of a natural gas versus a liquid. So the way we're going to do this is we're going to run a first law analysis, right? Because now we want to find what's going on with that thermal efficiency. So we're going to run a first law analysis on all of the different components. And because it's every process is an open process, we're going to use the open version of the first law, right? We'll say this is at steady state, one inlet and one outlet for all of these components. We're going to neglect kinetic energy. We're going to neglect potential energy changes. And then for each component, we're going to say it's either adiabatic or passive. We'll say there's no friction losses in between the different components and in the heat exchangers. And we'll say that there's no heat loss in the lines that connect the different components. If this slide seems familiar to you, it's because this is the exact same analysis that we did on the Rankine cycle. The symbolic part of this solution is exactly the same. So we're going to expect to get equations that look like the ones in the Rankine cycle, right? Unless I force you to maybe relax some of these assumptions and maybe there's heat loss from the compressor or something, right? But we're typically expecting, if we get power it's going to be the mass flow rate times H in minus H out, right? Hi-ho. And if we have heat transfer rates, that'll be the mass flow rate times H out minus H in, right? And we're expecting the turbine power to be positive, the compressor power to be negative, because the compressor's like the pump. And then we expect the combustor, that's where we're adding heat, we expect that to be positive. And where we're rejecting heat, we expect that to be negative. Now, this is where it gets different from the Rankine cycle, right? Because we got to say, what's the fluid? And the fluid is an ideal gas, right? So here's my Brayton cycle, right? I'm putting power in, right, in the compressor, right? So on the TS diagrams, for the open cycles, I think the TS diagrams tend to be more malleable. For the closed cycles, the internal combustion engines, I think the PV diagrams can be helpful too, because that really shows us the differentiation between the Otto and the diesel cycle, right? So then we're going to add heat here, and then we're going to get power out of the turbine, and then we're going to reject heat from the, the heat rejection part, right, into the atmosphere. This is what a Rankine cycle would look like if we ran the whole thing, right? If our vapor dome was down here, if we ran the whole thing way out past the vapor dome, right? Because that's basically what a natural gas is, right? Is we've moved so far away from the vapor dome that we can treat the gas as a natural gas. So this is what the Brayton cycle looks like. And it's important to know where the turbines and the compressors are, because that'll tell you where the processes, if they were ideal, where they would be isentropic, right? And anytime the working fluid is a natural gas, knowing where the isentropic processes is critical, because that will tell you where you can use your isentropic relationships to fix the states, right? So when we're adding and rejecting heat, we assume no friction losses. And if we have an ideal compressor and turbine, then we'll say that that's isentropic, right? Or we might have to know the isentropic efficiency, and then we can use the ideal outlet to find the real outlet, just like we talked about with Rankine cycle. Just like when we talked about internal combustion engines, if you were comparing two cycles and you drew them together, right, you can see that the area inside the TS diagram is the net heat, and the area inside the PV diagram is the net work, right? And those two things we know have to be equal. So one of the things that you can pick, right, is your compressor pressure ratio, which is hard for me to say. It basically says, how much do you increase the pressure when you go through the compressor, right? So again, that's hard for me to say. So let's assume that our maximum temperature is limited by, say, the steel that we're using, because we don't want our turbine to melt, right? That's probably a good thing, right? So if we go with a high compressor pressure ratio, so we increase the pressure a lot, then we'll come up here, but then we can only add heat till we get to this maximum temperature, and then we go through the turbine. But if we have a low compressor pressure ratio, right, we can go up to here, and we can add even more heat to get up to that maximum temperature, and then we come back down, right? So these are our sort of two different potential cycles, or at least two different potential cycles. So cycle A has a bigger compressor pressure ratio, right? And then it's more efficient. I don't know why they called it A and then labeled them 2' and 3' and 4'. I think that it should be the other way around, but I didn't write the textbook, right? So here, right, this one that has, if you get a bigger compressor pressure ratio, you get better thermal efficiency, right? If you're running a power plant, this is probably what you want, right? Because what you want to do, well, it just depends. You're the engineer, right? So you know what you're trying to do, right? Like anything with engineering, there's a trade-off. There's no one best answer that's good for every problem, right? Every problem is going to have some kind of a trade-off, right? So here, you can have a high compressor pressure ratio and get better thermal efficiency. But if you want more work or power developed, then maybe you want a lower compressor pressure ratio, because you'll have more area in your cycle. So, for example, we talked about using these Brayton cycles in airplanes, and we talked about using them in natural gas power plants. In an airplane, your power to weight ratio is probably your primary concern. You like efficiency, right? But the most important thing to you is keeping that airplane up in the air, right? So you want to generate lots of power and you want to be light, right? Because it's flying through the air. But if you're on the ground, maybe the thing that you really care about is efficiency, because this thing's gonna, you're gonna turn it on, you're gonna run it for a long, long time, right? And maybe the thing that you're really worried about is how efficiently can we run this system? Maybe that's your primary concern. Not that you're not concerned about power, right? Just like the aero engineer is still concerned about efficiency, right? But your primary goal is different, right? So you got this like slider, right? Or this lever, and this compressor pressure ratio is one of the levers that you can pull to try to find a good operating space where you're satisfied with the power that you're developing and the efficiency. But just like anything, like we talked about the Bugatti versus the, the Corolla or the Prius maybe, right? They have different goals, right? One is maximum power and the other is maximum efficiency, right? So you're trying to, you operate in different spaces and you make different choices depending on the product that you're dealing with, right? Or the problem that you're trying to solve, right? So as with anything in engineering, there's a trade-off, right? So you can pick more net work or you can pick more thermal efficiency, but you can't really have both, right? Usually to improve both things, you need some kind of dramatic change. Like you need to make up a whole new thermodynamic cycle. Right, so as an engineer, our job is to always know the application, right? And try to get decisions that fit the application, that are suitable for the application, right? So like I said, if you're trying to design an airplane, power to weight is probably the thing that you're most concerned about. So you might be more interested in your power and then you take the efficiency that you get. But if you're running a natural gas power plant, maybe you're less concerned with something like a power to weight ratio because your natural gas plant is not flying through the air, right? And maybe your primary concern is efficiency, right? But you're the engineer in this situation, right? You're the one that has to make the decision, right? Or at least argue for a particular solution if you're not the decision maker, right? Okay, so what do we do if we don't have ideal compressors and pumps, right? Because we know those things don't exist in real life, right? So reversible processes don't exist. There are no ideal compressors or ideal turbines, right? So we can still use these isentropic efficiencies because it's helpful to compare what's happening in real life to ideal things. And then we also have these efficiencies, right? So this is exactly the same as it was for the Rankine cycles, that for turbines, right, the power generation is a benefit. So the real thing gives us less benefit. So we put the real turbine power on the top and the ideal turbine power on the bottom. For the compressor, which is like a pump, this power is a cost to the system. So the real system pays a higher cost than the ideal system. So here we put the ideal compressor power on top and the real compressor power on the bottom. Again, you don't have to memorize these things because they're on the equation sheet. If we get the expressions that we expect and things are numbered in the way that they typically are in the textbook, then these would be the expressions that you get if you can make all those assumptions that we usually would make here. Right? So here we still want to be able to identify the isentropic outlets, right? The ideal outlets, because even if we don't need the ideal case, then we're going to use the isentropic efficiency to get to the real case. And we got to remember that to get these isentropic outlets, we're going to have to use our special isentropic relationships because the working fluid is an ideal gas. So let's go through an example. I'll see if I can get my writing tablet to work here. This is going to be an ideal Brayton cycle with 4 components. I think this is the right one. No. Here we go. Right, so here we have a Brayton cycle, right? So this is our Brayton cycle, and we have power coming in here at our compressor, power coming out here at our turbine. I'm just going to move this over here. We have heat going in over here. This would be our combustor, all CM, and this would be heat, our rejected heat. We're told some information about the system. We're told a value of K and a value of CP, although I just wrote this in myself. Typical values for CP for air in metric is 1, right? And typical value for K for air is 1.4, right? You can figure out CV from that, but I think it's 0.7 something, right? We're also told that the compressor pressure ratio is 8, but it didn't have to explicitly say that because here, right, our compressor takes us from 1 to 2, right? So to go from 1 to 2, that means that we go up 8 times. So that compressor pressure ratio is 8. It's always bigger than 1. We're also going to assume that this heat addition happens at constant pressure, and that the heat rejection happens at constant pressure too. Basically, this is going out to the atmosphere. This is coming in from the atmosphere. So that's the same pressure, 100. So I can just quickly fill out those pressures, even if I don't need them. We're asked to find the net power per unit mass and the thermal efficiency. So the first thing I'm going to do is try to find symbolic solutions. And then I'll go through and try to fix the states. So the net power per unit mass. So in order to do this, I have to do a first law analysis here on the compressor and on the turbine. So for the compressor and the turbine, right, we're trying to find these things, right? I could draw them like this. There's power coming out of the turbine, and there's power going into the compressor, right? This one is negative. This one is positive. So I'm going to use my first law here. I'm going to say that these components are at steady state. So this term goes away. That they're both adiabatic, because it didn't tell me anything about heat loss. That they're both one inlet and one outlet. And that I can neglect kinetic and potential energy changes, right? So I said steady state, adiabatic, one in, one out. And I'll say that delta KE is approximately equal to 0, which is approximately equal to delta PE. So all that stuff goes away. So then what I'm going to get is that the power from the compressor, which I know is negative, right? Both of these are going to be m dot times h in minus h out. So this is going to be m dot h into my compressor. This is state 1, 2, 3, and 4. So this is going to be h1 minus h2, right? But the book actually, the problem asked me not for w dot, but it asked me for w dot c over m dot, right? So I'm going to divide both sides by m dot, right? So this is going to be h1 minus h2. And I expect this to be negative, right? I'm going to do the same thing with the turbine. I'm going to get the same answer because I made the same assumptions. So this is also going to be m dot times h in minus h out. But h into the turbine, this was state 3, and h out of the turbine is state 4. So this one is going to be h3 minus h4, going to be less than 0. But the problem didn't ask me for these things individually. It asked me for the net power per unit mass, which is going to be just, I can call this little w dot net. This is going to be h1 minus h2 plus h3 minus h4. Right? These are negative, these are positive. This is good, but now I got to ask myself, well, I know the fluid is air. Right? And because the fluid is air, I got to say, is it constant specific heat or is it variable specific heat? And in this particular example, we're going to say that it's constant specific heat, which means that my delta H terms are going to become Cp times T1 minus T2 plus, well, why don't I, instead of drawing Cp again, I'm going to make it, because Cp will come out of this term as well. And this will be T3 minus T4. And this is W dot net per M dot, which is equal to little w dot. This is the thing that sometimes I get frustrated with thermo, is that we make a big deal out of how uppercase letters and lowercase letters are, it makes a difference. But then we pick letters like W and S. U, I guess you can put the little stick on the side, right? But a lot of these letters look the same when they're uppercase and lowercase. So this is a lowercase W, and this one is, maybe I'll go like this to remind myself that's a capital letter. Now the good news, I know Cp, and I believe that I know the even numbered temperatures. Let's go see if I know. I think I know T1 and T2. So I know T1 and T3, and I don't know the odd numbered temperatures, T4 and T2. So I got a symbolic solution for part A. I don't have the ability to get numbers yet because I don't have those numbers. But let's pretend that this is an exam and I totally blanked on how to fix these states. That's okay. I'll go to the next part and I'll start working on how to get the symbolic solution for the next part. Right? And then we'll come together at the end and try to fix the states, right? Which is always my preferred method when you're in a time-constricted environment, right? So, you know what's great about thermal efficiency is that this is going to be little w dot net. So here, if w dot net, little w dot net, is equal to big W dot net over M dot, right? And little Q dot net, or Q dot in, sorry, is equal to big Q dot in over M dot, right? Then I can say that this is equal to little w dot net times M dot divided by little Q dot in, this is net, times M dot. I can cancel out these mass flow rates. And what I find out is that it doesn't matter what the mass flow rate is if what I'm looking at is the isentropic efficiency or the thermal efficiency, right? Because here for the thermal efficiency, it's mass flow rate independent because all of these mass flow rates are the same. So I already have, the good news is I already have this, right? I just did that in part A. It's like the person who wrote the question knew that it would be helpful to me, right? But I need to find Q dot in. So here in my cycle, Q dot in happened between state 2 and state 3. There's some heat coming in here. Right? So for this component, I'm going to say that it's at steady state, that it's passive. This is 0, this is 0, that it's one inlet, one outlet, no kinetic energy change, no potential energy change. Right? One in, one out. Delta K E is equal to 0, which is, I guess I should always say approximately equal potential energy, right? So now I'm going to get the expression that I would expect here as Q dot in is equal to M dot H out, which is state 3, H3 minus H in, which is state 2, right? Or if I want little q dot, right, is just going to be this divided by M dot, which is going to be H3 minus H2. Or now if I say I'm going to assume a cold air standard analysis, or if you prefer, you can say that this would be constant specific heat. Then here we could say Q dot is equal to Cp times T3 minus T2. Right? And this is my denominator. Right? So now when I go back to my thermal efficiency, this is going to be little w dot divided by little q dot, right? Little w dot was Cp times 8, sorry. Because I put the Cp in here, it's not an H anymore. It's going to be T1 minus T2 plus T3 minus T4 divided by Cp times T3 minus T2. My Cp's are going to cancel out. I look at this, and just like before, I don't know the odd numbered temperatures, but I do know the even numbered temperatures. Sweet, right? Because now I've got a symbolic solution for part B as well. Right? So now I got 5 minutes and I'm going to try to fix all the states, right? But there's only 2 more states that I got to fix and I already know the pressures. Right? So here I'm going to cheat over here. Where's the, at least I'm going to try. Where's that? Oh, the window's behind here. I'm going to bring down my state table. So the thing that I'm trying to get ultimately is I want the temperatures. Right? So I want state 1 first. Awesome. I already have state 1, right? Because it's given to me. I know the temperature and the pressure. And if I'm doing a constant specific heat analysis, temperature and pressure are the only things that I need. So now here, because it's an ideal gas, I need to know which are the isentropic processes, right? So this is an ideal compressor, which means delta S is equal to 0. So as I move from state 1 to state 2, this is an isentropic process. So I could call this, instead of state 2, I could call this state 2S. Although in this case, there's no isentropic efficiency, so I don't have to differentiate it that way. But this reminds me that I can use an isentropic relationship. So now what I would do is I would go down, let's see if did I include equations at the bottom? No. So I would go to my equation sheet if this was an exam, and I would look for some equation that's going to tell me something like T over T is equal to something that has K up here in the exponent. Because this is an open system process, I typically know pressures, right? In the internal combustion engine, I knew the compression ratio, which was a volume ratio. But here, for a Brayton cycle, I know the compressor pressure ratio, which is a pressure ratio. So if I want to fix state 2, I will say that temperature at state 2S divided by temperature at state 1 is equal to the pressure at state 2 over the pressure at state 1. And now the exponent is not just K, it's K minus 1 over K, right? I can rearrange this because the thing that I actually want to find here is T2S, right? So this becomes T2S is equal to T1 P2, I can call it P2S if I want, P1, K minus 1 over K. What do I know about this temperature? It's got to be in absolute, right? Anytime you're dealing with an ideal gas problem, my advice is use Kelvin or Rankine. Sometimes you'll have a delta T, but you might as well just do it, and then you won't make a mistake. Right? So this temperature, we know this is the compressor pressure ratio. This is R, which in our case is equal to 8. Right? It told us that P2S was 800 kPa and P1 is 100 kPa and K is 1.4. So if I put this stuff into my calculator, I get that T2 is equal to 543 Kelvin. State 3, I already know T3 and P3, so I can skip right to state 4. But again, I can call this 4S because this is the isentropic turbine. Delta S is equal to 0. So now I can say that T4S over T3 is equal to P4S over P3 to the power of K minus 1 over K, right? Or I can do this and say that T4S is equal to T3 times P4S over P3, K minus 1 over K. In the turbine, the pressure is going down. So here, this is 1 over 8, right? I put this in, and I get that my T4 is 938.5 Kelvin. So now that I know T2S and T4S, I can go back up here. I find that my thermal efficiency ends up being 44.8%, and that my net power per unit mass, which I have an expression for up here, right? Because now I found these temperatures, right? This is going to be 520.7 kilojoules per kilogram. And that's how you do a basic Brayton cycle that was at constant specific heat. A wrinkle you could get, so you could get isentropic efficiencies on the turbines or the compressor, right? Or it could be variable specific heat, in which case the flow chart looks the same, but when you do those isentropic processes, you have to use not an expression with K in the exponent, but something that's P over P is equal to PR over PR. So you have to use the variable specific heat version. And then there'll be some interpolation on table A22, right? You'll find the temperature at state 1, which will let you find PR at state 1. And then you'll use the ratio of PRs because it's an isentropic process to get to state 2. That'll give you PR2. You use that to find H2 and then then T1. And then you do that same process back and then forth in the turbine as well. So that's all that I have for you today. I'm happy to answer any questions, though. If people have any, you're welcome to stick around.
All right, thank you.
No problem. Thank you.
Thank you, Professor.
No problem.